Hi Year 10, this is our last lesson for logarithms, and in this video we're going to look at all of the applications of logs. Let's look at what we've learnt so far. We've learnt how to define logs, how to change from index form to log form and vice versa, all about the log laws and the change of base rule. Then we learnt about log graphs, and then finally how to solve equations using logs. Now there are so many areas where logarithms are used that it's hard to know where to start. Here's just a couple of them: finance, biology, statistics, chemistry, and physics. So let's begin with a finance problem. One invests $4,000 into an account that bears 4% per annum interest compounded annually. For how many years must he invest in order to accumulate $6,000? All right, so we're going to start with our compound interest formula. A is equal to P, and then 1 plus r in brackets to the power of n. Now let's substitute in what we know. We know that the amount accumulated is 6,000. The amount initially invested, or the principal, is 4,000. 1 plus r is going to be 1.04, and we don't know n. Now, this used to be a question that we had to do by guess and check, but we don't need to do that anymore because we can solve an exponential equation like this. We need to get rid of this 4,000 first, though. So do 6,000 divided by 4,000, gives us 1.5. Take logs of both sides. I'm going to do log base 10. Now, I've done something sneaky there. Can you see it? I've moved this n down the front all in one go. You can do an extra step if you want to. Divide both sides by log 1.04. And so n is equal to log of 1.5 divided by log of 1.04, which is 10.3 years. Here's another example, this time from archaeology. Carbon-14 dating can be used to determine how old a fossil is. You've probably heard of this. When a creature dies, the amount of carbon-14 starts to decay. If we know the amount that's left, we can figure out how long the creature's been dead. Here's the formula. It's a bit confusing. Let's go through it. So in the formula, T is the time in years, P0 is the original amount of carbon-14, and P of T is the current amount of carbon-14. You'll also notice that it's got the natural number in it, E. E is approximately equal to 2.718. Here's an example. A fossil is found to contain 30% of its original carbon-14. How old is it? So the problem with this question is that we're not told how much carbon-14 there was originally or how much remains. We're only told a proportion. But that's okay, this is what we can do. If P0 is the original amount of carbon-14, then 0.3 lots of P0 is what remains. And that's what we're going to substitute in for P of T. So this is the current amount here. And you can see how the P0s will cancel out, and we're left with just an exponential equation that we can solve using logs. Now you can take logs of both sides. Some people, once they learn how to do that, that's all they do, and that is perfectly fine. But we do have log base E on the calculator, so I could just turn this around into log form. It will be log base E of 0.3 is equal to negative 0.00012 t. Dividing both sides by this number here, and I get that, and putting it into the calculator tells us that the fossil is 10,033 years old. Now those previous two examples were about using logarithms to solve exponential equations, but there is one other main area where we use logarithms, and that's with graphs, and particularly with log scales. Now you would have seen this recently in the news. Here's a graph of the coronavirus cases, and this is a linear scale, and you probably saw next to it that there was a logarithmic scale that you could look at. And you probably clicked on it and then wondered what the difference was. Okay, well, it's pretty easy to understand. Let's have a look at this one on the left. This is a linear scale because it goes up by the same amount each step. So this is going up by 500,000 each time. The logarithmic scale, however, multiplies by 10 each step. Do you see that? Times by 10, times by 10, times by 10. Now, the reason that we do this is it takes out this exponential part of this graph, okay, because at this point here we can't see if anything is changing. Okay, because it's sort of flattening the curve here, we can see that it's going up, but then it has a period of success, and then it increases again, and then we're starting to flatten it out again. It's still going up. There are still, new cases every day, but currently here on April 15th, it's starting to flatten out again. So one of the main reasons that we use log scales, well, there's two reasons. The first reason is to take huge numbers and be able to put them into a single graph, because these numbers are very large. And the second reason is to flatten out this exponential part so that we can actually see what's going on. So logs can be used to straighten curves. And this is a technique that's particularly used in the sciences, and you'll probably see it in years 11 and 12. There are two types of curves that we can straighten. Power curves, that's where we've got x to the power of something like x squared. And exponential curves, that's where we've got something to the power of x. And these graphs both look fairly similar, except this one goes through 0, 0, and the exponential curve doesn't. So let's have a look at the new cases of coronavirus in the USA. So this is up to April the 15th. We can see that we've got an exponential growth happening here, because this is a linear scale. And then it sort of flattens off. Okay, there's ups and downs, but there's no more exponential growth, if that makes any sense. All right, we're going to take this part of the graph here and then graph the log of the number of cases, and I'll show you what will happen. So here's that selected data, just using a linear scale. And you can see how it is increasing at an increasing rate, so it's exponential. So let's have a look what happens when we graph the log of the number of new cases. So just in Excel, I've done the date. I've labelled it day 1, 2, 3, 4, 5, etc. And this is the number of new cases. And then I've taken log base 10 of this number. Okay, and we're graphing this column here against this column. And look, we pretty much get a straight line. It's sort of in two bits, can you see that? Okay, up until this point here, it's got a steeper gradient, and then it sort of flattens out a bit. So they were getting a little bit more control of it, even though it was still exponential growth here. But here it was sort of like a runaway train. Okay, so there are some famous logarithmic scales. Richter scale, pH scale, and sound intensity are three of them. Let's have a look at them. Earthquakes used to be measured using the Richter scale. They're not anymore, and the new formula is also logarithmic, but it's a little bit more complicated. So I'm just going to stick with the Richter scale. Here's the formula. M is equal to log base 10 of A. Now, M is the magnitude, so the size of the earthquake. A is the amplitude of the ground movements during the earthquake. Now, amplitude means the size of the trough or the peak of the wave. So that's the amplitude there. Now, since the Richter scale is a logarithmic scale, this means that an earthquake measuring 9.0 is catastrophically stronger than an earthquake measuring 4.5. This is something that people don't really understand about logs. It's not double the intensity, it's 31,623 times stronger. Let's have a look at the maths. How strong is an earthquake that measures 9.0? So here's our formula. So this is the value for M. Okay, so it's going to go in here. Now I want to work out the amplitude of the ground movements. So I'm going to turn this back into index form. 10 to the power of 9 is equal to A. How strong is an earthquake measuring 4.5? Okay, so instead of having 9 in here, I'm going to have 4.5. Okay, how much stronger is this compared to this? So I'm just going to do 10 to the power of 9 divided by 10 to the power of 4.5. 31,623. Here's another logarithmic scale, the pH scale. In chemistry, it measures the acidity or alkalinity of solutions. Here's its formula. pH is equal to negative log base 10 of M. M is measured in moles per litre, so that is the concentration of hydrogen ions in the solution. Okay, and you'll notice that this is going to be a negative log. You'll also notice that it's log base 10 as well. Calculate the concentration of hydrogen ions per litre in the following liquids given their pH value. So blood has a pH value of 7.4, and so what we want to do is work out how many hydrogen ions there are per litre. All right, so there's our formula. pH is equal to negative log of m. So we're going to put the 7.4 in here. Okay, now we want to turn that around so that we get m as the subject, but I need to get rid of this negative first, so I'm going to bring it over here. Okay, 10 to the power of negative 7.4 is equal to m. There's our answer. 10 to the power of negative 7.4 moles per litre. What about soft drink? It's quite acidic, so it's got a pH of 3.0. It's the same method. pH is equal to negative log of m. Substitute in 3 for our pH value. Take the negative over. 10 to the power of negative 3.0 is equal to m. So soft drinks got 10 to the power of negative 3 moles per litre of hydrogen ions. So how many more times acidic is acid rain that has a pH value of 3.5 compared to normal rain that has a pH value of 5.6? All right, acid rain, let's put the pH in 3.5, taking the negative over and then turning into index form. M is equal to 10 to the power of negative 3.5. Normal rain, doing the same method, m is equal to 10 to the power of negative 5.6. So how many more times acidic is acid rain? So we want to do 10 to the power of negative 3.5 divided by 10 to the power of negative 5.6, so 126 times more acidic. Okay, so here's our last one, measuring sound. The intensity of sound relative to the minimum level of sound that's audible to the human ear. So that's I0. That's called the threshold of hearing, by the way. It's given by the formula S is equal to 10 multiplied by log, and then it's got this ratio I over I0. So S is measured in decibels, and I over I0 is the ratio of the sound to the minimum sound audible to humans. That sounds really complicated, but I'll show you an example to show you how to use this formula. How many times louder than a car, which is 70 decibels, is a helicopter, which is 100 decibels? All right, so we'll start with our formula. Now, where does the 70 go? Remember how I said S is measured in decibels? So it goes in here. So 70 is equal to 10 multiplied by log of I divided by I0. So what we want to do is make this the subject. So we're going to divide both sides by 10 and now turn it into index form. So 10 to the power of 7 is equal to I over I0. Okay, so that means that a car is 10 to the power of 7 times louder than the threshold of hearing, so the minimum sound audible to humans. Okay, let's do the same thing for helicopter. So I've substituted the 100 in. Just going through the same process, I'm going to get I over I0 is equal to 10 to the power of 10. That means a helicopter is 10 to the power of 10 times louder than the threshold of hearing. So how can we compare them to one another? How many times louder is the helicopter over the car? We're just going to do 10 to the power of 10 divide 10 to the power of 7. So it's 1,000 times louder. And that brings us to the end of this topic for logarithms. It's a really important topic for years 11 and 12, so spend some time and make sure that you master it.